Okay. Thank you so much. I'm very glad to be here. Thank you so much for the invitation. And I will be here for the entire workshop, and I'm very happy to chat with all of you with topics related to this, but also about others. Like I know that there are many people here interested in quantum learning, fermion system, bosonic systems. So yeah, feel free to reach. Yeah, I'm super happy to chat, interact with all of you. Okay, so the title of my talk is The Complexity of Noisy Quantum Circuits, or better, the complexity of, sorry, okay. Okay, maybe this doesn't work. Okay, it's good. Okay, perfect. Or better, the complexity of most noisy quantum circuits. Because, yeah, like the complexity of noisy quantum circuits, as we'll see, is already quite understood thanks to fault tolerance, but we'll go in detail later. And this talk is mostly based, oops, sorry. This talk is mostly based on this work, noise-induced shallow circuits and absence of barren plateau. And I will also mention results from this other paper that Armando already presented. And okay, and these I share work with these awesome collaborators, Shumik, Sumit, Jens, Daniel, Hihue, and also I had the very nice pleasure to collaborate on the second paper with Armando, Manuel, Marco, and Zoe, that is also the Armando and Zoe are here as well. And okay, so spoiler of what we will see. We'll see that if we have a circuit like this, where this is any basically realistic noise, only the last layers matters to estimate expectation values of observable for most circuits. And this implies that the complexity of most noisy circuits is very low. And also that we'll see that these typical circuits are also classically simulable, even if they lack so-called barren plateau that you have heard about by Eric also this morning. And okay, that's the spoiler. And the outline is a bit introduction and motivation of why we should care about noise in quantum circuits. Then I will talk about the complexity of noisy random circuits. I will explain this result. Then the classical simulation of these circuits. And then I will stress that noise model matters, like that, for example, the picture about barren plateau is changed if you change noise models. And okay, let's start. Okay, and also please interrupt me if you have any questions at any point. Yeah, like I think I have time to address questions also during the talk. I'm happy that is interactive. Okay, then understanding the impact of noise in current near future quantum device is important for harnessing their capabilities. People now are designing algorithms, but so far we have not fully fledged fault-tolerant quantum computer. So designing algorithm with taking account noise is important for being realistic. And many previous works, many of them model the noise as depolarizing, which is like easy, arguably easy model to have handle some analytical calculation. And however, like also it's not arguably there are also some other source of noise in realistic quantum device, like photon emission, like atom loss, some sorts of non-unitality that, for example, the max MX state is not fixed by realistic noise model always, and this is this map fixes the identity channel. And it has been shown that depolarizing noise is catastrophic for quantum computation. For example, induces barren plateau in variational quantum algorithms. And also implies, it has been shown that these quantum supremacy experiments by Google become classically simulable if you incorporate depolarizing noise into the picture. So yeah, basically depolarizing noisy circuits are known to be easy, like for many proposed applications. And but time departures from this model could lead to different conclusions. For example, as was like already observed in this paper, Quantum Refrigerator by Benor, Gotzman et al., in which they analyze fault tolerance under different noise models. And also in this paper that discuss that this algorithm for random circuit sampling does not work if you have, for example, amplitude damping, this classical simulation algorithm, and also the hardness proof for random circuit sampling break if the noise is different from the polarizing. Okay, so yeah, let's say that if outside this noise model, little was known. And the polarizing assumption, if true, enormously constrains noisy computation. In fact, it's very well known that if you have any circuit of depth L, like with depolarizing noise, and let's say that the depth is larger than log n, you have a fast convergence to the maximum mixed state, like yes, this basically implies that circuits after log n are exponentially close, are more they're they're polynomially close to the maximum states. So basically, in order, like quantum computation, useful quantum computation is possible only for log n depth under the polarizing noise. Because if you have the circuit is more than log n depth, you just sample from the maximum state that you can do classically. And so also Pauli expectation value, for example, of these circuits are easy if you have larger than log n. That is like you can just output 0 and you have asymptotically exponential precision. And yeah, so basically the classical simulation of all deep depolarizing noisy circuits is somewhat trivial because most of the time, if you want the Pauli expectation value, you just output 0. And if you want sampling, you can just sample from the uniform distribution. And yeah, like if you have less than log n, you can also do, for example, some light cone arguments if you have 1D or, I mean, in 2D, 3D, it has been recently also shown that in average case, these are easy. Yeah, like, but let's say that there in for deep circuits, classical simulation is somewhat trivial because you just output 0 for Pauli expectation value. For smaller circuit in geometrical connectivity, yeah, like light cone arguments are good, quite good. Yeah, so basically the picture for the polarizing noise is like before our work was more or less full understood what is like the easiness of noisy circuits, like the complexity of noisy circuits. And okay, sorry. So I said to you that these circuits in most regime are classically simulable. Oh, sorry. However, now we know that fault tolerance exists. And so these noisy circuits should not be classically simulable. So now I ask you a questions like what enables fault tolerance? How can we resolve this? I mean, we have fault tolerance, quantum error correction that says that if the noise rate is low enough, we can, this circuit should not be classically simulable. BQP arguably is different from BPP. Many people believe so. So what is missing in this model? So, exactly. Yeah, like Sofia said, the entropy extraction. Like the polarizing noise is a noise that basically is entropy increasing, called also the entropy increasing. And the unitary gates do not change the entropy of the state. So basically, this converges to the maximum state. In order to enable fault tolerance, something very important is put out entropy from the system. So in all this fault tolerance proof, what people, what they need, a minimal assumption, is to have some auxiliary state here, like some fresh auxiliary qubits, some fresh qubits during the computation that, they are used to put out entropy. Yeah, if you reset the qubits, basically you cool down your system. So these are necessary for like having fault-tolerant quantum computation. And okay, so reset operation during the computations are what enables fault tolerance. And these are necessary for depolarizing noise. Okay, and yeah, so entropy must be removed. And without resets, quantum computation with depolarizing noise is possible for log n depth, as we said. And this inequality holds fast convergence towards the maximum states. However, for noise different from depolarizing, not all circuits become trivial after log depth. And for example, if we have amplitude damping, also a small amplitude damping component, very small, this is not anymore true. And you can have, it has been also argued that this showed that these circuits can make, are complexity theoretic, from a complexity theory point of view, very powerful. There is, if BQP is different from BPP, you cannot simulate these circuits with amplitude damping and depolarizing, as I will mention more detail in a bit. Okay, and also, as we mentioned, real hardware noise is not solely depolarizing, which is a type of unital noise. And for example, we have T1 error, amplitude damping, which are so-called non-unital, where this identity does not hold. And as the result that I was referring before about that these circuits are non-trivial, it's I was referring to this paper, Quantum Refrigerator, which shows how to make fault tolerantly a circuit without fresh auxiliary qubits. Basically, the idea is that okay, like basically, I told you before that with depolarizing noise, you have to have fresh auxiliary qubits. If the noise is non-unital, like amplitude damping, you don't need these fresh auxiliary qubits. The idea is just that if you have amplitude damping, for example, or like some probabilistic reset, you can just let some qubits cool down. I mean, you can just let some qubit not interact, let them converge to the fixed point, that is 0, and then you have your fresh auxiliary you can put, and so you can create your fresh auxiliary for yourself. And use the previous known fault-tolerant construction. Okay, please, you had the what's? What, sorry? You say to avoid the strong limitations of the depolarizing noisy circuit. Yeah, I'm saying that also, by the way, if you have amplitude damping but you don't do anything to take advantage of it, it's also, not clear if it's more useful than depolarizing. In fact, as I will show later, we show that for most choice of the circuit, there is no preference of having amplitude damping or not. Yeah, yes, from a worst case point of view, amplitude damping is better, but we will show that for typical circuits, there is no reason to prefer, amplitude damping. Yeah, so yeah, but yes, you can artificially reset a qubit if that's helpful. Okay. So non-unital noisy circuits can be made fault tolerant even without reset operation. That's the thing. And so the complexity of these circuits is, is believed to be the equivalent to BQP. Okay, so one can carefully engineer the circuit to perform reliable quantum computation. You can choose these gates carefully to perform a very hard computation, and these states are non-trivial. And so if BQP different from BPP, for example, observable expectation values cannot be estimated classically efficiently. However, what happens for generic typical noisy circuits? This is the content of our work. For example, let's say if we take uniformly at random the unitary gates, 2-qubit unitary gates, what happens? Okay, this is the content of our work, our works. And so what happens for generic noisy circuits? We first show that only the last log n layers matter for most circuits to estimate expectation values. And the intuition is that if nothing clever is done to remember the information, I mean, you lose the information, like if you think to resetting qubits, like the content of these gates will be forgotten once you go deep enough. So yeah, if you think the probability of not being reset it's lower, I mean, a lower, like, so you can have an intuition why this phenomenon emerge. Like, yeah, we show this for any noise, but yeah, for example, resetting with some probability each qubits, you can see quite easily why only the last few layers matter. Okay. And so to make the comparison with depolarizing, in the depolarizing scenario, no layers matter for deep circuit. And for non-unital noise, we show that the last log n layers do matter. Okay. And in mathematical terms, what we show is that for any initial state rho 0, like if this is your target expectation value, and O is your observable interest, and phi rho 0 is, I mean, the circuit applied to initial state, you can have, like, just retaining the last k layers of your circuit, you can have an exponential precise estimate of your target expectation value by putting any preferred initial state. Also, if rho 0 is exponentially complex, you can just put any input state here, and your error scales exponentially. Yes, it's any noise that is, the only assumption is that it's not a gate, it's not a unitary, it's not, we assume that it's not a unitary channel. Okay, I mean, probably in the paper, we say it's IID, but can be, in fact, the referee asked this as we are updating. Yeah, one can, yeah, like, yeah, like remove this assumption from, it's not, that's not, yeah, I mean, for example, you can say that you can remove the assumption and say that the maximum I mean, you can have in terms that the worst or the easiest noise should be, I mean, like basically we have that there is, yes, we can have, I had the assumption the noise parameter in our proof should be labeled, but I mean, they can be different. I mean, like if the channel, if all the noise are not unitary, it's all okay. What, sorry? Like this, I mean, like that this local noise channel should not, yeah, still local, should not be okay, equal. It can be different. Yeah, like for if you ask about correlated noise, like yeah, like there, okay, we didn't write down, but like I think a similar proof technique works. I mean, the proof techniques is just, I mean, working the Heisenberg picture, understanding, I mean, the action on the noise map with respect to the Pauli transfer matrix of the noise channel. I mean, it's just instead of having a 4x4 parameterized channel, you have, for example, 16 by 16, or I mean, sorry, you have a 2-qubit channel. And yeah, it's just I think that also for single qubit channel is somewhat probably weaker than intuition. Wise also correlated noise should work. Is that correlated noise 2-qubit channel is also something that can be worse than single qubit. So yeah, I expect that yeah, one can say, for example, yeah, like similar stuff that I'm saying for yeah, correlated noise. Please. If I got that correctly, as the theory is any potential state, regardless of what proceeding is. But then I think doesn't mean that basically the circuit does the same thing to all the round. Yes. Like basically, you just forget really what happens before the last. I mean, basically, you can you forget the information of this sigma 0. Any sigma 0 give you the, I mean, the same result under this approximation. Yes, you have exponentially in k decaying error, and any sigma 0 has the same yeah, number under this error bound. This half sigma 0 and this potential probably you got the n sigma 0. Oh yeah, here you can put also the max over sigma 0. Like I mean, this equation holds for any sigma 0. This inequality. So basically, you can really choose. You want to estimate this. Basically, what I tell is choose any initial state. For example, product state, 0 state. Take the last k layers, and yeah, that's and estimate the expectation value. And okay, and also the dimension. Okay, this average here is over the probability distribution underlying this circuit, this uniform random gate, and can also be translated with high probability, like via standard inequality like Markov. Like one can translate this with yeah, with the probability, with high probability, this statement holds. Yes. Okay. Yes. There is another question. If you've not done anything, you've not changed the parameters of the gate last L-K gate. Say, cut this circuit at some point, ignore the first half, and put in end state, and you get the same expectation value. Yeah. This should be interpreted like take a circuit with high probability over the choice of these gates. Only the last. I mean, if you retain just the last k layers, you have a good approximation. Yeah, it's just that for most circuits, this happens. Yeah, this like with high probability over the choice of these gates, this inequality holds without expectation. Yeah, but when yes, I mean, I'm just saying if you pick from the distribution, underlying distribution, that is, they are measured over these 2-qubit gates, this circuit, yes, you can just retain, with high probability, you can just retain the last few layers. Oh. No, I'm just saying by applying what you get by applying Markov or Chebyshev to this like I'm just saying that yeah, with 1 minus delta probability, yeah, like one can have, yeah, we'll mention more later. Yes, yes, but this is an average, and you can go from probability, from average to probability statement through Chebyshev Markov, but yeah. Yeah, like but we can make this precise later. And okay, so this follows from the more general theorem, that is this where yeah, we have Pauli And yeah, same circuit, two different input state, and here we have exponential decay with the Pauli weight. I mean, also we can show that yeah, exponentially. I mean, the also Pauli with high Pauli weight. Sorry, if you want to estimate high weight Pauli expectation value, yeah, you have exponential suppression to for yeah, high Pauli weight with the Pauli weight, and yeah, and also this implies that for deep circuits, for linear depth circuit, I mean, we have trace distance convergence between two state rho and sigma, and in exponentially in L, where L is the depth of the circuit. And crucially, here we assume that the depth is at least linear, and this is actually an open question. If we can make it this log n, like basically for the polarizing noise, it happens that for L larger than log n, this inequality is true. Basically, but from our proof technique that is just proof using a corollary of this, of this inequality, like from Binius one norm, yeah, like leveraging this inequality, we can prove that from linear depth this happens, but actually I think one should be able to prove from log n. For L larger than log n, this should happen. And yeah, if anyone is interested, yeah, this is an open question. And this would also prove in the strongest notion that, yeah, average case noise, general noisy circuits are somewhat similar of the polarizing noisy because yeah, after log n, the states in trace distance become similar. And yeah, a general result like this, but without expected value, cannot be obtained, as I said before, because of fault tolerance construction. So yeah, one may wonder, yeah, but expected value results are boring because I care about a fixed circuit. But yeah, in this case, you cannot really remove this if you want some triviality statement. And yes, however, in certain eigennoise regime, we can obtain it. I mean, there is, for example, fault tolerance requires low error rate. One can say for higher error rate what happens. And actually, yeah, we can prove some statements like this. In this case, we can say that for R larger than log n depth, very noisy and qubit circuit, and any state rho and sigma, we have this result for any input state rho and sigma. Yeah, under some definition of very noisy that we have in the paper, that if the noise rate is high enough. And okay, so also this implies, this result already implies immediate algorithm for simulating these expectation values. Because if we want to estimate trace p phi rho 0 with high probability over the choice of phi, and this maybe also answer now your question. Like so the task is I sample a circuit, like I choose my circuit drawn randomly, and I ask, okay, this is the circuit with noise. Can you estimate this Pauli expectation value with high probability over the choice of the circuit? And from what we saw before, it's like one solution that one might have is to output just the result for last k layers. And we showed this. And so if you want epsilon precision, just the log epsilon minus 1 layers suffice to have this epsilon precise. And yeah, so basically, so if you have a log epsilon minus 1 circuit depth, you can work in the Heisenberg picture. And if the Pauli is local, then if the circuit is also geometrically local, this observable will be also local. And you can use so-called light cone arguments to estimate your observable expectation value. And yeah, if this k depth circuit and like in 1D, for example, if this is local, this will be also supporting the order k qubits, and which can be computed efficiently for light cone arguments, at least for 1D. And so the computational time for 1D is just the computational time to estimate, to simulate quantum computation that is exponential in the number of qubits involved. And here it's exponentially k, that k is log epsilon minus 1. So we have a Pauli epsilon minus 1 runtime for 1D. And to solve this task. And so the statement more formally is that given a randomly sampled noisy quantum circuit for any depth and noise, there is a classical algorithm to estimate the local Pauli expectation value up to epsilon additive precision with high probability over the choice of the circuit. And the runtime is exponential log to the d epsilon minus 1, where d is the spatial dimension of the system. That for d equal 1 is Pauli, epsilon minus 1, otherwise it becomes to be quasi-Pauli. And we had no dependence by number of qubits and depth for epsilon, if we leave epsilon not dependent by n, of course. And so for constant precision epsilon, the algorithm is efficient for any dimensionality. Like it does not depend by number of qubits if we are interested in constant epsilon, like 10 to the minus 4. And but for epsilon inverse Pauli, the algorithm is efficient for 1D architecture and quasi-Pauli for D larger than 1. And and I said here local Pauli expectation value, but for global Pauli expectation value, there is nothing to simulate because one can just output 0 and succeed with high probability. Because for typical circuits, the output Pauli expectation values of where the Pauli is as a Pauli weight that is grow with 10. Yeah, the Pauli expectation value is exponentially decaying with the Pauli weight. And yes, we also give, this I think also some people was interested in this morning. I mean, we give like basically these are all average case statement, but one can say, yeah, but I care a specific instance. Can you also check if the classical simulation succeeded somehow? I mean, we give a condition to verify the success of the classical simulation. That is check that if the Heisenberg value observable is close enough to be proportional to the identity. However, yeah, we would like to prove something else along these lines. That this happens also with high probability. But yeah, these but we believe that this is also for most circuits satisfied. So basically, oops, sorry. Basically, if you want to simulate a noisy circuit, a strategy that works most of the times is just retaining the last few layers. And you can check also that if these last few layers are sufficient for estimating your observable expectation value. Okay, and so simulating Pauli expectation value in noisy random quantum circuits with Pauli n-1 accuracy into the the open question was this from our work, that the algorithm for inverse Pauli accuracy is inefficient, like it was quasi-Pauli in 2D and all-to-all connectivity. And inverse polynomial accuracy is very important if one wants to estimate, for example, ground state energy of Hamiltonian. I mean, if you want to have some error that scales with the system size. Yeah, so I mean, this was a very important open question. And 2D circuits are very important. I mean, for example, Google main architecture are 2D. So yeah, this was a very important open question. Please, do you have a? Did you say? No, it's 2D or larger. Yeah, it's just that I could have added the 2D, 3D. And then, I mean, but actually, yeah, I mean, I think 2D is the most interesting because all-to-all, I mean, I don't know, it's 2B is also a bit not super realistic because the qubits needs to be interactive. You can move qubit around, but you have to connect them. Yeah, so 2D, 3D, it's our word. So yeah, I don't know, like it's you can see this in 2D, 3D. That is super important regime. And luckily, this question was solved by this amazing team of people, including Armando and Zoe here, and using this Pauli path propagation algorithm that was introduced this morning. And basically now, for solving this task, we can just say poly n epsilon minus 1 without any requirement of the geometrical connectivity. And as again, we don't have depth dependence of circuit architecture. And the algorithm is based on Pauli path truncation, as I said. And also the intuition is that Pauli weights are suppressed. So so basically in your light cone simulation also, it's useless to really take care of all the Pauli. I mean, one really needs to just, if the Pauli, high-weight Pauli do not matter exponentially suppressed, you better not consider them. So that's the intuition. If you do lot cone simulation, you can also disregard them. And okay, so also the idea, as you heard this morning, is working the Heisenberg picture and cut by weight. And okay, also a very amazing numerical simulation were done by Manuel Rudolph, a student of Zoe, and I was super happy to see, amazed to see this large scale simulation, and that shows that these algorithms work for more structured circuits, and I mean beyond this random distribution assumption. And also this I found very cool that he really did this large scale simulation for large scale systems, and showed that this algorithm performs very well. Okay, and okay, so this is about the complexity of noisy circuits, of most noisy circuits, and we show that basically on average these circuits are not if typical circuits are efficiently to classically simulate. There is no quantum advantage, like if you want to simulate typical quantum noisy circuits. And and also basically, even if you have amplitude damping, connecting to your question, there is no, if you don't really engineer your circuit, there is no real reason to prefer amplitude damping to depolarizing. Both of them are classically easy for expectation value observable. So the second topic that I will talk about is barren plateau. Sorry, how much time do I have? It's 30. It's on. How much? Okay. Okay. Yeah, good. Okay. So basically, okay, barren plateau you have heard already, but let me just phrase the problem. Is variation quantum algorithms are they encode the problem into the minimum of a cost function that depends from the parameters of the gates. And for example, you have these parameters, you can parameterize your gate U1, U2M. And barren plateau is the problem where you start you find yourself in a landscape that is flat. And so it's basically with high probability under this initialization procedure, I find myself in a flat landscape that is difficult to navigate, especially with quantum computers, because under this paradigm, you have to estimate the expectation value, but if you have to take exponentially many shots to understand if it's zero or not, it's a problem. And okay, so barren plateau, the definition is that for most choices of U1, UM, the cost landscape is flat. And cost functions are made by Pauli expectation values often. And so one can also ask what variation in the gate do to the cost function. And relevant quantity is the partial derivative to harness this. And so if the variance of the partial derivative is exponentially small, then the influence of these gates is very unlikely. And in QML terms, people also say that this definition of trainability that yes, this under yes, as Eric mentioned today. And okay, so what was known before is that for noiseless circuits, barre and plateau emerge at deep enough depth, like super logarithmic or linear depth. You have exponentially like vanishing cost functions or partial derivatives. And this is also due to the fact that I mean, if these gates are initialized randomly, and this is also due to the fact that these circuits becomes approximately true design, like, then, and also this means that the gates are not trainable. And in the depolarizing noise regime, it was shown by a group of Los Alamos that also these holds even, I mean, you don't need even randomness. I mean, for worst case circuits, after log n, you are exponentially close to the maximic state, and the maximic states have zero expectation value. So yeah, I mean, you don't need also average assumption for this type of statement in the polarizing noise. But for non-unital noise, we show that we don't have barren plateau at any depth for local cost functions. That means the variance is always omega 1. But we also show that this is only due to the last few gates, the few layers. And so only last few gates are trainable, and so this trainability, this lack of barren plateau is only like it's a disappointing lack of barren plateau. Please? Shallow? Yeah, we didn't, this interesting. We didn't explore local minima, but yes, I think we have the evidence that, in the precise sense that we have in the paper, like expectation value, observable, these are effectively shallow. With respect to their form of consideration, like sampling, or this might, but I believe that, yes, in the strongest sense, you can assume that these are shallow. So in shallow circuits, like you can borrow the results that are known for shallow circuits in the local minima. But yeah, I think that many things would fall out easier if you have this trace distance convergence. Okay, yeah, this is the picture that we show for trainability. And only the last log n layers are trainable, because if you pick this k equal log n or above, you can have super poly vanishing. And also another paper came out around the same period that had similar observations by Singh Kanipa and Daniel Lidar. Okay, so yeah, we show that exponential suppression in Pauli strings, like in the variance, and the local cost function do not suffer from exponential concentration, for example, Z1, while global cost function do. And the theorem regarding the partial derivative in most formal terms is this, that we have also an exponential suppression in the Pauli weight. And if P local, then we have this. Otherwise, and also implies large gradients norm. And if P is global, we have exponentially vanishing. Okay, and for particular case of unital noise, our tools imply this, and this improves a bit about upon the previous result over unital noise, because this extend also to dephasing noise, for example. Dephasing noise is not unital, but is also not a type of channel like depolarizing that is entropy increasing. So our tools allow us to prove this, that Yeah, it's for unital noise and for any unital noise. And okay, the proof ingredient I already mentioned, work in the Heisenberg picture, to design property of 2-qubit gates, normal form of the noisy channels that also Armando mentioned this morning. That is a parameterization that made calculation a bit easier. Okay, so numerical experiments confirm our results for more structured circuits, like using QAA ansatz or symmetric circuits. Yeah, the conclusion is that any amount of non-unital noise induces lack of Barren plateau, but it truncates most circuits to effectively logarithmic depth, allowing efficient classical simulation in estimating public expectation values. And so a way of reading this result is that unless we carefully engineer the circuits to take advantage of the noise, it's unlikely that you prefer non-unital noise with respect to depolarizing noise. Yeah, at the beginning of my presentation, I said that depolarizing noise, no matter what you do, you are easy to log depth, but with amplitude damping, there are these fault-tolerant construction like quantum refrigerator that in the worst case, you can do very difficult stuff, but in the average case, we show that, there is not really advantage. And yes, because we show this effective depth picture, log depth is with depolarizing noise. And so it's also unlikely that non-fault tolerant noisy quantum circuits provide any quantum advantage for observable expectation value based algorithm. And also assuming overly simplistic noise models could be misleading with, like, for example, as we saw for Barren plateau. And the open question is the complexity of classical simulation or random circuit sampling with non-unital noise, as discussed in detail in this paper. And yeah, the depolarizing case was shown to be easy in this QAP plenary talk of a few years ago. Yes, so the open question for amplitude damping is open, or for non-unital noise. Okay, thank you so much for your attention. So thanks for the talk. So we have time for a few questions.
Any chance that all your information gets fixed down equals here for sampling, or if
What, sorry? If
found information gets fixed down equals here for sampling, or if
okay, like honestly, I mean, I don't know. Like, I don't know if I mean, I think there might be chance. I don't know personally. We tried a lot with Armando as well to think if can be said something. Ah. Okay, for the Schuster paper. Mhm.
we have some idea about how
Mhm. Okay, yeah. Mhm. Yeah, like yeah. You mentioned the Schuster paper. Yeah, this has been reference that unfortunately missed. Yeah, I should have put that. Is was in its crucial paper, and actually also he answered. He and his co-authors answered also the question that I mentioned at the beginning. That like actually I was a bit. I said here log n is a maximic state, so it's easy to simulate, but smaller the log n, what happens? In 1D, Litecoin suffice. In 2D, 3D, Litecoin are too weak. And actually, you cannot have polytime algorithm in 2D, 3D. Because I mean, and under some complexity or assumption. So one can ask, what about average case circuits? And this paper came out last summer, answered that yes, for the polarizing noise, average case circuit are easy, and also for some class of non-unital noise. However, while for amplitude damping, that is also mentioned in the Thomas Schuster paper and all it all. I mean, for sampling, there is no. I mean, so far I'm not aware about sampling results for these kinds. The Bill Pfefferman paper says absence of anti-concentration. That is a property that is used for like in the basically in the proof of basically this paper here, sorry, of Aranov et al. They use a property of the circuit called anti-concentration, and this is not satisfied if the circuit has a non-unital noise, but is satisfied if it has like the polarizing noise or slightly deviation. And also hardness proof. Hardness proof to say, like people believe that random circuit sampling, like exact is is the almost exact, like is hard. While yes, for and even with the polarizing noise, but I think this was a paper by Dalzell et al. But for non-unital noise, the paper by Pfefferman says that also the hardness proof do not hold if you have non-unital noise. But that's a super interesting question if Pauli path propagation can be adapted to sampling, and also okay, I know that Armando taught a lot about this and Zoe, so we can chat later more about this.
Sorry, I have a question about this point, but even though there is no formal proof, what do people expect?
Okay, to be honest, I would say okay, no, sorry. I would expect. I mean, I could be wrong, but I would expect that sample. It's not different from the polarizing. I mean, yeah, like, but I might be wrong.
I actually have another big question. When you mentioned the barrier plateau, the lack of barrier plateau for non-unital channels, so what are the assumptions? Because if the channel is fast mixing, or somehow if they thermalize very quickly, with that barrier plateau.
Actually, okay, like basically intuition is that okay, let me say. Basically, if you have like some, I mean, think about some non-unital channel. It's something like that you can it's basically entropy non-increasing, like it can decrease entropy. So for example, you should be able to have some resetting component. If you have some non-zero probability of being reset, I mean, some gates at the end will matter. Like the probability of this qubit being resetted, it's can be low, but it's still a constant. So I mean, it's basically this parameter here, it hides some non-unitality component. Like for example, is omega 1 hides the strength of the non-unitality, basically. So you have a small, I mean, basically, if you think in probabilistic reset picture, it's one can see that the probability of being resetted before, I mean, of not being resetted is high, is a constant. I don't know if I transmit the intuition about this result.